The sublimation curve explain the process of steam formation at constant pressure. You have looking here, you have in a cylinder arrangement. You have in first, you have in just you have in a water is there and the of weight is there. That is the formation of the steam. What is will be indicated this formation of steam? The vertical line will be indicated T saturation and horizontal line will be indicated enthalpy. Totally, this will be represented in TH diagram. This TH diagram, the initial having sensibly, then latent T, then superheated form of heat. The steam formation, the steam is generally formed at a constant pressure. Consider 1 kg of water. I'll be taken 1 kg of water in 0 degrees Celsius in a cylinder with pressure P maintained. That is the heat supplied in Q and that weight will be measured W. See, when the energy supplied to the temperature of water increase until uh, reaches the saturation temperature of boiling water, corresponding to the pressure P maintained on the water. This is the T saturation. Next, volume of water increases in liquid due to heat addition. Uh, quantity of quantity of heat added water during the process. HF is equals Cw into Ts. See, this is the initial condition of that is the sensible heat the 0 to A. The 0 to A is having sensible heat and A to B is latent heat and B to C is superheated form of heat. See, HF is equal to enthalpy of saturated water with 0 degrees Celsius and Cw is specific heat of water. Further, heat addition changes the phase from liquid to vapor state. When the part of water remains in liquid form, but major part of converter into vapor from the steam is known as volume because water is getting converted into steam as shown in the figure. The further heat addition remaining part of water gets evaporated into steam. It is to continue till all the liquid is completely evaporated in steam as shown in figure. 0 to A to B, and B to C. First one you have in a T saturated, then T superheated, that is degree of superheat. See here, there are three form of steam heats here. First one will be wet steam, next will be dry steam, next will be superheated form of steam. The wet steam of enthalpy will be represented in next that is very very important. Drainage fraction of steam. What is meant by drainage fraction of steam? The wet steam is a mixture of saturated by water and steam. The relative amount of each which are present in such two phase of mixture determine the quantity of mixture. Drainage fraction of steam is defined the ratio of mass of dry saturated steam to total mass of mixture. Drainage fraction of steam is defined the ratio of mass of dry saturated steam to the total mass of mixture. It is generally denoted by X, mass of dry steam to it is the ratio of mass of dry steam to mass of wet steam. Uh, it is calling about drainage fraction of steam. The drainage fraction can represented by X symbol. Uh, This is the separate link calorimeter. The separate link calorimeter have the main component is the steam main. This is the steam main. Next, you have in sampling tube with the per perform perforations and control valve. And this is the pressure gauge. And next, you have water quantity indicator tap. See here. Uh, Perforated cup and inner chamber, outer chamber, and two barrel calorimeter. See, this is the separate link calorimeter. In this calorimeter, the drainage fraction of steam is determined by separating the water particle associated with the wet steam. Arrangement of this calorimeter shown in figure. This is the separate link calorimeter. Wet steam at pressure P. You have in here the initial you have in wet steam that pressure P made it to pass through the sampling tube from the steam main control valve. This is the main control valve, uh, which kept fully operated. The steam coming out from the steam main tube stick against of the perforated cup, which called separator. See here, you have once that wet steam, the water particle with steam passes through the your perforated cup. Once that cup passes through the wet steam and water, the whatever steam particle is there that will be moving from the upwards, that will be moving for the upwards, the water will be collected to the downwards, then that will be indicated from water level indicator. When steam strikes against the separator, it undergoes the quick reversal direction of motion. The water particle present in the wet steam due to greater inertia get separated from the wet steam and get controlled at bottom of inner chamber. The amount of water those separated is measured with the help of water quantity indicator. The mass of water is denoted by MW. The separated dry steam is finally condensed and its mass measured which denoted by MS. The drainage fraction measuring the separating calorimeter mass of dry steam to mass of mixture. That is MS, mass of dry steam to MS and MW. This is separate link calorimeter. Next, that is very, very important in the point of view in the examination, combined separating and throttling calorimeter. The steam main, this is the steam main, this is the pressure gauge. You have here mass of dry steam and mass of superheated steam, mass of water and mass of steam, both passes from the main your your cup. See what happens to once the water particles with the steam passes through the cup. Whatever steam contain is there that you have in the steam contain that will be flow from upward direction, and water will be collected to the downward in the water level indicator how much water will be storage in the storage tank. Then you have here the pressure gauge 1. The pressure gauge 1 will be indicated in the more pressure to compare the pressure gauge 2. The pressure gauge 2 also have some amount of pressure is there, then passes to the that is the throttling calorimeter. This throttling calorimeter you have indicated is thermometer in the temperature indicator, and then throttle valve. Then you have a throttling calorimeter, then it will be manometer. See here, what happens to the combined separating and throttling calorimeter to measure the pure, the very pure form of superheated steam in outlet of throttling and separating calorimeter that will be represented in a few the pure superheated form that will be Hg plus Cp T superheated minus T saturated. Combined separating and throttling calorimeter is separating throttling units arranged in a series combination is used for accurate measurement of drainage fraction of wet steam. See why you have using in especially from in your separating and throttling calorimeter to measure. It is used to accurately measurement of drainage fraction of wet steam. In this arrangement, a sampling pipe having a transverse holes around the circumference is inserted into the main pipe, which is carried the wet steam P1, whose drainage fraction has to be determined. Next, the sample of steam those obtained passes through the separating unit through the control valve. The This valve is kept fully open so that steam may be undergo any throttling stage. Here, the calculation part of when the steam is made straight against the prepared cup, it undergoes a quick reversal of direction in its motion. The water particle in steam have greater inertia. Therefore, due to this sudden reversal of direction out of mixture, the amount of water though separated is collected and measured. The remaining dry steam is now made to pass through a throttling unit where while passing through the throttle valve, it is great throttle constant enthalpy. Steam pressure is measured before and after throttling. Temperature of throttle steam also measured. The throttle steam coming out the throttling calorimeter is then condensed and calculation of a separating and throttling calorimeter. M is equal to mass of wet steam sample from the steam made. M1 is equal to mass of water particles separated and collected in a separating unit. M2 is equal to mass of steam condensed and weighed after. A drainage fraction of wet steam, considering the separating unit. The amount of water separated in separating unit 1 minus x1 into m 1 minus x1 m1 plus m2. Let x2 be the drainage fraction of steam entering the throttling unit. Amount of water carried steam into throttling unit 1 minus x2 m2. Now if x be actual drainage fraction of steam in the steam main, the amount of water content initially in the steam 1 minus x m1 plus m2 from the law of conservation of mass 1 minus x m1 plus m2 equals 1 minus x1 m1 plus m2 plus 1 minus x2 into m2. Divide both sides of equation by m1 m2. 1 minus x equal to 1 minus x plus 1 minus x. 1 minus x 1 minus x plus 1 minus x into x 1 minus x is plus x minus triple x is equal to xx. Therefore, the actual drainage x of wet steam in the product of drainage fraction determined by the separating calorimeter and throttling calorimeter. The numericals during a steady flow process, the numerical is very important in the drainage fraction of steam. And one more important of fluid substance. During a steady flow process, 4 kg of steam at 15 bar and 260 degrees Celsius losses 3771 kilojoule of heat at constant P pressure. Determine the final condition of steam. Mass of steam 4 kg, pressure 15 bar, temperature 260 degrees Celsius, heat loss 3771 kilojoule to find the final condition of steam. To find out the values from the steam table in 15 bar, the saturated temperature is 198.3 degrees Celsius. We show the initial condition of steam is superheated and the enthalpy of the superheated steam. H superheated is equal to Hg plus Cp, T superheated minus T saturated. To find out the superheated form of enthalpy, Hg plus Cp, T superheated minus T saturated. See, I've taken 15 bar, Hg value is 2789.9 kilojoule per kg, constant pressure 2.1 kilojoule per kg Kelvin, and H superheated is equal to 2789.9 plus 2.1 into 260 minus 198.3. See here, you have in H superheated temperature, and this is the values of H superheated is equal to 2919.47 kilojoule per kg. You have in 4 times 4 into H superheated, the total enthalpy of steam. In heat loss at constant pressure 3771 kilojoule, remaining enthalpy of steam 1976.72. As per pressure constant to measure H2 is equal to HF plus X2 HFG. You have find out here drainage fraction 52 58.2%. Total 100% you have 51.8% is water, and remaining you have in superheated form of steam. You have find out the using the formula and steam table. See the second problems. Throttling calorimeter as the steam entering into its at 10 MPa, coming out at 0.0 MPa and 100 degrees Celsius. Determine the drainage fraction of steam. P1 is equal to 100 MPa is converted into bar, and next HF1 is equal to 1408 kilojoule per kg. HFG1 is equal to 1319.7 kilojoule per kg. P2 is equal to 0.05 MPa equals 0.5 bar, and TS is equal to 81.35 degrees Celsius. Cp is equal to 4.18 kilojoule per kg Kelvin, and Hg equals 2646 kilojoule per kg. From 1 to 2 is throttling process. H1 is equal to H2. HF1 plus X1 HFG1 equals Hg2 plus Cp. T superheated minus T saturated to find out the X values. See here, draw the simple Rankine cycle on PV and TS diagram, TS and HS diagram. Steam enters at 80 bar and 450 degrees Celsius in steam turbine. Expand isentropically up to condenser pressure of 0.1 bar. Find the state of steam at turbine exist and power developed by the turbine. P1 is equal to 80 bar and T1 is equal to 450 degrees Celsius. P2 is equal to 0.1 bar. Flow rate of steam 5 kg per second. P1 is equal to 80 bar and H1 is equal to 3270.2 kilojoule per kg, and S1 is equal to 6.511 kilojoule per kg. At P1 is equal to 0.1 bar and HF 191.8 kilojoule per kg, and HFG 2392.9 kilojoule per kg, and Hg is equal to 2584.7 kilojoule per kg. S1 SF 0.649 kilojoule per kg Kelvin, and SFG 7.502 kilojoule per kg Kelvin. SG is equal to 8.151 kilojoule per kg Kelvin. Please look at here. Yes, SF plus X2 SFG to find out the X2 values, and next to find out the H2 values 2058.26 kilojoule per kg. To find out power developed by the turbine, the work done during the turbine, mass into change in enthalpy. You find out the mass flow rate 5 kg per second. Okay, the fourth problems, a steam turbine operating on a Rankine cycle receives the steam at pressure 20 bar. You have in P is equal to 20 bar. P equals P equals 20 bar. And next you have a degree of superheated steam, degree of superheated steam, superheat, the degree of superheat P sup equals 89 degrees Celsius. And next the exhaust pressure 0.07 bar, the exhaust pressure P equals 0.07 bar, and expansion steam takes place isentropically. To calculate expansion steam, take isentropically, calculate heat supplied, the Q will be calculated, and assuming the feed from supplier of water to the boiler 20 bar, heat rejected in the condenser and work done by the turbine. See here Ts is equal to 212.4 degrees Celsius. To convert it into values from the Kelvin. Temperature of superheated steam, Ts is equal plus degree of superheat. T superheated is equal to 212.4 plus 89. To convert it to the values from the Kelvin. From the steam table to take the, you have in, there are two ways to take the values. One will be temperature base, another one will be pressure base. You have take the values from the temperature base. Ts is equal to 212.4 degrees Celsius. Temperature of superheated steam, T superheated plus degree of superheat. T superheated is equal to 212.4 plus 89, 301.4 degrees Celsius. T superheated is equal to 574, 574.4 Kelvin. See here, the diagram can represent the vertical line will be temperature, horizontal line will be entropy. See here, that is there in the wet steam 3, 4, 5. It's the wet region. 5 to 5 dash is there in the dry region, and 5 dash to 1 is the superheated region. This is the TS diagram of in your pure substance. Here, enthalpy H superheated is equal to H1, Hg plus Cp, T superheated minus T saturated. From steam table in 20 bar, Hg is equal to 2792.2 kilojoule per kg, and Sg values. These are all the values will be taken from the steam table. Then substitute the enthalpy of superheated 2984.1 kilojoule per kg. Entropy S is equal to S plus C ln T1 by T2. Then you will find out the S1 values 6.6895 kilojoule per kg. For isentropic expansion process, S superheated is equal to S2, S superheated is equal to S1. Next, you will find out the values 6.6895 equal to SF2 plus X2 SFG2. You find out the values. X2 is equal to 0.7949. Now work done by the pump is equal to HF4 minus HF3. Next, the important question from the pure substance. Explain with neat sketch of phase change pure substance. Define the following terms: triple point, enthalpy of wet steam, critical point, and dryness fraction. Draw a net sketch separating and throttling calorimeter. Explain how dryness fraction determined. Draw a net sketch of throttling calorimeter. Explain how dryness fraction is determined. This is the theoretical questions from the pure substance. Problems on properties of pure substances. A throttling calorimeter is attached to the steam pipe, carrying the steam pipe 11 bar. The pressure and temperature of the steam after the throttling are 1.2 bar and 120 degrees Celsius. Uh, find the drainage fraction that can be measured under above condition. Take Cp equals 2.1 kilojoule per kg Kelvin for superheated steam. The following data were obtained with a separating and throttling calorimeter. The pressure in pipeline 1.5 MPa. Condition after throttling 0.1 MPa at 110 degrees Celsius. During the 5 minutes of moisture collected in the separator 0.15 liters at 700 degrees Celsius. Steam condensed after the throttling 5 minutes 3.24 kg. Determine the quantity of steam in the pipeline. A vessel having a capacity of 0.05 meter cube contains a mixture of saturated water and saturated steam at a constant temperature 270 275 degrees Celsius. The mass of liquid present is 10 kg. Find the following pressure, the mass, the specific volume, specific internal energy, specific entropy, and specific enthalpy. These are all major questions from pure substance. Thank you.